Hi, my name is Thomas Zulper, and this is a case study of a Lockheed-Martin C-130 Hercules aircraft, which is used for heavy equipment transport across vast stretches of land and water. The presentation is geared for my ME 4730 thermal fluid system design students, and it serves as review material from their fluid mechanics class, wherein we study fluid power equations. So we're going to start off with a bit of a review of just the different types of airfoils and fuselages that are used on modern aircraft to attain certain performance goals. And you can see by the illustrations of various birds that there's a lot of similarities between the shapes of the birds and the modern day aircrafts. For example, the flycatcher on the left has to have great maneuverability to actually catch a fly, and that's not unlike the maneuverability required by a fighter aircraft such as the F-15. In the second instance, the Swallow is known for its very high speeds, and so we see some slender swept wings, and it's somewhat reminiscent of the SR-71, a spy aircraft used that relied on very high velocities to perform its functions. Another type of spy aircraft that relied on high altitude rather than speed is the U-2, which you can see very closely resembles the albatross, a bird that's known for attaining high altitudes and in some instances circling the Earth over and over again. So it needs high distance and long range in order to evade, in this case, the missiles from the Soviet Union. But the rightmost is most reminiscent of what we'll be looking at today. It is a bird, or in this case an aircraft, that is known for lift capabilities. So we can see the C-130 resembles the Hawk in some respects. The Hawk is designed with very high lift wings, so it can dive into some water, grab a fish, dive onto land, grab a rabbit or something like that, and carry it away. Now the reason I'm going with the C-130 and the high lift ability is because it simplifies some of the aerodynamic analyses that would be particularly complicated in a case study of something like a fighter jet or a very high-speed aircraft like the SR-71. So we're going to keep it relatively straightforward in this case and go with a very popular and long-lived C-130 aircraft. I think first delivered in 1955. Now it's 2025, so it's seeing 70 plus years of successful use, not only in military applications, but in humanitarian aid and a range of other uses. So the original purpose of the C-130 was to deliver heavy artillery essentially across the ocean to what was the Korean War battlefield. And while it needed to do multiple jumps for refueling, it was nonetheless designed and specified to carry very, very heavy loads up to 75, even 100,000 pounds of munitions, such as that tank shown there. So the assignment for students in my ME 4730 class are parts 2 and 3 of what I've listed here. Today we're going to go through part 1, which was a final lesson in my ME 3300 fluid mechanics class, and this is serving as a review and a lead-in to ME 4730 thermal fluid systems design. So today we're going to size the engines to allow a C-130 to carry 75,000 pound force of load over 1,500 miles at a velocity, a constant cruising speed of 350 miles an hour. And the next parts, part 2 and part 3, are to size the engines required for the aircraft to actually take off at an even heavier load with a relatively short runway of 3,750 feet. And then with the information on the power of the engines required to perform that takeoff, we're going to actually design the engines and while we're studying the Brayton cycle in thermal fluid systems design. So let's start off with a little review. All the information on the C-130 used here is all publicly available. This data is a screenshot of information at the military website, kind of giving the overall dimensions: a wingspan of almost 133 feet, a length of almost 100 feet, a height of almost 40 feet, and then what we have here is the wing area or planform area, which we'll be using to calculate wing lift and wing drag. Then we have other information such as the empty weight of 75,800 pounds. This is just the airframe without any additional load. And then we can add in a useful load of around 72,000 pounds. Now, it can actually go up to nearly 100,000 pounds under wartime conditions, but for present purposes, we're going to focus just on a 150,000 pound aircraft in the majority of the calculations done here. Now we have further information on the power plant. It's got 4 Allison T56 turboprop engines. These have actually been replaced by Rolls-Royce, or I should say Allison was bought out by Rolls-Royce, so they've rebranded the engines. Still a T56, but you can see the 4 engines listed in this frontal view right here. And we actually already have the information or the answer to the calculations that we'll be conducting today, but we need to see the intermediate steps and why it is that we end up with these values. And the propeller diameter, you can see here as well, is this 13.5 feet diameter. Very large propellers, a rather imposing aircraft, and we want to understand its performance characteristics. Now, further excerpts from online information show not only the dimensions we've looked at already, but also what type of airfoils are being used. So these are 2 types of NACA airfoils. You can see one type is used on the tips, and that is this area right here, what we'll refer to as the wing tips. This is obviously a blended NACA airfoil going from a large chord length to a relatively short length. And then you see at the root where the wing attaches to the fuselage, we've got this NACA airfoil with a constant chord length. Chord length is this dimension right here, attaching it to the fuselage. Now, because the majority of the aircraft is actually comprised of this NACA 64318 airfoil, we're going to just assume that it gives the lift and drag characteristics of the entire wing, and we're going to disregard this for present purposes while maintaining the same planform area, A sub P, as you'll see in a little bit, for the entire aircraft. Now, we can look up the NACA airfoil lift and drag coefficients from this handy website, Bigfoil, right here. And the data comes out really as raw data, which I replotted in Excel to show the lift coefficient and the drag coefficient as functions of angles of attack of the aircraft. Now, I want to point out, in building this aircraft, the angle of attack is kept at 0 for ground level, or we'll say horizontal flight, not necessarily on the airfield itself, but also in the sky. And so if we go to a 0-degree angle of attack, trace the line up, and then go to the left, we can find a lift coefficient of 0.26. Likewise, if we go to 0 angle of attack and go up and over to the left, where this red line intersects the axis right there, we can see a drag coefficient of the wing of about 0.011. We'll be using these airfoil performance or lift and drag coefficient charts a few times over the 3 parts of this case study. But we're going to start off with an angle of attack alpha equal to 0, and we're going to draw our numbers of 0.26 and 0.011 for horizontal flight of an unloaded aircraft. Now, another thing we want to consider is there's a multitude of efficiencies and tables of data that we need to make use of. These aircraft have variable pitch propeller blades, which can go everything from fully feathered to locked, you can see a shift of angle of upwards of 90 degrees. They can even go past 90 degrees and provide some reverse thrust if it needs to back up on the runway. Now, these variable pitch blades end up having variable efficiency in their ability to convert shaft power to fluid power, and we're going to take the conservative estimate of 50% for all instances, just to ensure that our engine is over-designed for the performance requirements. So this is the case study that I give to my fluid mechanics students, junior level mechanical engineers, as we work on the aerodynamic chapters of the fluid mechanics textbook. So here we'll be reviewing this. We're given a fully loaded C-130, uses NACA 64 A318 airfoils, and flies in calm air. That is to say, the wind velocity in the region is 0 miles per hour or feet per second, and it flies at a constant altitude for 1,500 miles. We chose the altitude of 20,000 feet, and the aircraft has the following dimensions and performance requirements. So we also want to make an assumption that the momentum flux correction factor is 1 in this case. We'll be looking at a variant of Newton's second law, referred to as conservation of linear momentum equation, which is used to calculate the thrust of this aircraft. Typically for turbulent flow, it can be something of the order of 1.05. For our purposes, we're just going to set it at 1. Now, we already saw that the empty weight of the aircraft is 75,800 pounds. Kind of nominal loaded airplane is around 150,000 pounds. That can actually go up to 175,000 in wartime conditions. We saw a blade diameter of 13 feet 6 inches, 13 and a half feet. We saw the cruising speed of 350 miles an hour. We're working with an altitude of 20,000 feet, which will give us the air density of 0.04077, listed right here, pound mass per cubic foot. The wingspan of nearly 133 feet. The planform area used for wing lift and drag has the subscript P to tell us its planform area, in contrast to frontal area of the fuselage, which is 225 square feet. That would be, if you were to make effectively a circle of the fuselage right there, that would be our frontal area, as opposed to the planform area of the wings, which is right here, A sub P. Beyond that, we saw where we got the lift coefficient for horizontal flight, angle of attack of 0 degrees, and we also saw where we got the drag coefficient for horizontal flight. Now, I looked up through a variety of resources and found the fuselage drag coefficient of 0.020, so that's where that information will be drawn as well. And then you saw on the propeller chart that we're going to take a conservative estimate of 50% propeller efficiency, and then this is a turboprop aircraft, or the 4 engines on the aircraft are turbine-driven propellers, aka turboprops, and the typical efficiency for a turbine is around 30%. We're just going to use that as a nominal value for now. Now, these aircraft, nowadays at least, run on JP8 fuel, which has a specific energy or energy content of 135,000 British thermal units per gallon. That's the information we need to move this from the very first portion of the exercise to the very last portion. So let's start with the calculation of lift force of the empty aircraft. So we're going to ask, or in fluid mechanics, I have the students find all of these calculations. We're going to review those because I'm not teaching fluids this semester, so it's a lead-in for thermal fluid systems design. So using our lift coefficient at an angle of attack of 0 degrees, we want to find the lift force. Then we'll look at wing lift coefficient at total weight. So the majority of this exercise is actually based on the total weight of 150,000 pounds. We want the angle of attack required there. We want the wing drag force, fuselage drag force, required thrust, total mass flow rate through the propellers. This V1 you'll see as the presentation proceeds is based on the incoming velocity. V1 right here is equal to 350 miles per hour, as opposed to V2, which is the velocity of the air coming out of the propellers after it's been energized or after it's been powered by the propellers. And we're just looking at this as an exercise in contrast to determine that we actually need mass flow rate from the air exiting the propeller rather than the air entering the propeller, which is just the speed of the aircraft. Then we get to propeller shaft power, which we saw was around 4,500 horsepower. In the information that's available online, but we want to do the actual series of calculations needed to confirm that. And then we also want to figure out how many gallons of fuel, of this JP8 fuel, is necessary to carry it a distance of 1,500 miles. So let's start off with just the airspeed of the aircraft itself. So we know that it's flying at 350 miles an hour to the right, and the ambient air is 0 miles an hour. That is to say, it's a calm day with no wind. So what happens in this case is that the aircraft induces a wind velocity on itself. So despite the solid object moving 350 miles per hour to the right, if we put our control volume around the aircraft, we can say air is entering the control volume to the left, from the right to the left, at 350 miles per hour. So this is our aircraft speed. And then we're still looking, we have to do some calculations to find our velocity of the air exiting the propellers right here, the V2, but we'll get to those equations soon enough. Let's take a look, however, at the forces acting on the aircraft. On the one hand, we have the force of lift holding it in the air. It's the product of the lift coefficient times what's referred to as the dynamic pressure, 1/2 rho v squared, and then times the planform area, the area of the wings as viewed from above. Now that counteracts the weight of the aircraft. If the aircraft is not accelerating upward or downward, then that means its acceleration is 0 and that the force of lift is equal to the weight either of the empty aircraft or the total weight of the loaded aircraft. So this would be the summation of forces in the y direction. We'll see soon enough. And now we also want to look into the summation of forces in the x direction. So to do that, we take a variant of Newton's second law, referred to as the conservation of linear momentum equation for steady state operation, and we want to simplify that to a form that gives us the force of thrust is the product of mass flow rate through all four propellers times the change in velocity from the downstream velocity, V2, to the upstream velocity, V1, right here. Now, in order to maintain constant velocity with no acceleration forward or backward, we'll say A is equal to 0, then we know that the force of thrust has to counteract the force of drag acting on the wing, this product of drag coefficient of the wing, dynamic pressure, and planform area of the wing, as well as the drag force acting on the fuselage, this product of drag coefficient of the fuselage, dynamic pressure, and frontal area of the fuselage. So let's jump into it. We'll start with the summation of forces in the y direction. And as we saw, y direction is equal to, summation of forces is equal to 0. So all we have to do is say the force of lift counteracts the force of weight. So we could rewrite this as summation of forces is equal to force of lift acting upward minus the weight. We're starting with the empty aircraft is equal to 0. Therefore, force of lift is equal to weight of the empty aircraft for the very first step of this problem. Now we want to work in pound mass, feet, and seconds in this equation, so we need to take our velocity of 350 miles per hour and multiplied by 5,280 feet per mile. Let me replace this. Mile per hour divided by 3,600 seconds per hour. So this gives us a airframe velocity, or a V1 velocity, of 513.3 feet per second. And we'll be using this through the remainder of calculations to stay within the pound mass feet second system used commonly in the United States. So let's start with a calculation of the force of lift at 0 degree angle of attack. So here we've got force of lift is equal to lift coefficient times 1/2 rho v squared, this will be V1, and planform area of the wings. So we saw at 0 degree angle of attack, we've got a lift coefficient of 0.26 times 1/2 times the air density of 0.04077 pound mass per cubic foot. And then we need to multiply that by our V1 of 513.3 feet per second, quantity squared, times 1745 feet squared. So this then gives us a force of lift of 2,436,812 pound mass feet per second squared, which is not a unit of pound force, the units that we need our force of lift in. So we need to do the unity conversion ratio, where 1 pound force is equal to 32.2 pound mass feet per second squared. And this then tells us we have 75,678 pound force is equal to the force of lift of the empty aircraft with an angle of attack of 0 degrees. Alpha is equal to 0 degrees right here. So we got the first answer for our multitude of questions, and now we want to proceed to the lift coefficient for the loaded aircraft, which does have an angle of attack associated with it. So this is in part an exercise understanding the lift and drag coefficients as functions of angle of attack for the NACA airfoil that we'll be using. So again, we saw that from the summation of forces in the y direction is equal to mass times acceleration, which is 0, that the force of lift minus the weight is equal to 0. So force of lift is equal to weight of the aircraft if it's in horizontal flight without elevation changes. Now, rather than the empty weight of the aircraft, we want to use the total weight of the aircraft. So force of lift, which is equal to total weight, which is equal to 150,000 pound force. So let's rearrange the lift equation and calculate the lift coefficient for the fully loaded aircraft is equal to the quotient of the lift force, that is to say equal to the weight of the aircraft times our V1 squared times our planform area. So this takes the 150,000 pound force, the weight of the aircraft, plus the full load. And now we have to undo our unity conversion ratio that we saw above, and we'll find that we need to now multiply by 32.2 pound mass feet per second squared for every 1 pound force. And so this ends up being our modified numerator. And then our denominator remains this 1/2 times 0.04077 pound mass per cubic foot times our velocity of 513.3 feet per second squared times our planform area of 1745 feet squared. So this gives us a lift coefficient of 0.515 is equal to the force of lift acting on our wing. So we have the lift coefficient that happens to be the second of the problems requested. And now we can go to our tables and we can look for the 0.515 that we just calculated and then draw a line from there over to the intersection of the blue line right here, and then drop down and find that our lift coefficient is required to keep the aircraft in level horizontal flight, requires an angle of attack of 1.8 degrees. Now, knowing that the aircraft is tilted at 1.8 degrees, we can go find the drag coefficient by taking our 1.8 degrees, following this upward to the intersection with the red line here, which we then trace over here, and we find our drag coefficient of the wing is about 0.012. So we just worked through the first three calculations. We found that for the unloaded aircraft at 75,800 pounds, that is to say at an angle of attack of 0 degrees for the wing, using the lift and drag coefficient shown there, that we calculate that it would produce 75,678 pound force of upward thrust, or of upward lift force on the aircraft, thus holding it in the air. And we could say the difference between 800 and 678 is negligible, 1% variation or so between the two values. So we can confirm our answer. And this obviously intended as an illustration to allow you to check the results. Now, our second set of calculation was actually done in the total, using the total weight of the aircraft. And we found that the airfoils themselves have to be pitched up. Rather than an angle of attack of 0, they have to be pitched up an angle of attack of 1.8 degrees, obviously exaggerated in that illustration there. But nonetheless, this then tells us what tilt the aircraft has to be adjusted to ensure level flight. Now let's proceed on to the wing drag force at total weight. And so that calculation makes use of the drag coefficient, the wing drag coefficient that we saw previously, the one we extracted from the table. We saw this is taken from the 1.8 degree angle of attack. Likewise, we need the wing drag force, the fuselage drag force, actually that doesn't change. And we saw, of course, the wing lift coefficient at that angle of attack as well. But we will be making use of the fuselage drag coefficient, which was the 0.020, and then this drag coefficient is the 0.012 that we have for the fully loaded aircraft. And present calculations in this presentation are going to be based on the fully loaded aircraft now. This, again, was our 513.3 feet per second. And now we're going to figure out the force of drag on the wing, force of drag on the fuselage, and then the thrust force required to maintain steady velocity. That is to say, acceleration is equal to 0 feet per second squared on this aircraft. So let's start off with just our force of drag on the wing. Force of drag on the wing is equal to our drag coefficient of the wing, which we read from the tables, times our 1/2 density velocity squared planform area. So 0.012 times 1/2 times 0.04077 pound mass per cubic foot times 513.3 feet per second quantity squared times planform area of 1745. Feet squared. So this gives us a force of drag acting on the wing of 112,468, and we roll our units through. We've got pound mass feet per second squared, which we again have to convert to pound force. This is a step that trips up many people in the calculation of force from mass times the acceleration in this case, the units we get in pound mass feet per second squared. So this then gives us a drag force on the wing of 3,493 pound force is equal to drag force of the wing. And students in my class know that I like them to put boxes around their answer, so I encourage you to get in the habit of doing that, certainly for your homeworks and exams in this class. Now let's do the same calculation, but in this case for force of drag on the fuselage. Notice that subscript F for fuselage rather than W for wing. So it's an identical equation with the exception of different values for drag coefficients and areas of the object. So again, we've got our 1/2 density velocity squared. In both cases, this is V1, the induced airspeed of the aircraft. And now we use frontal area. So running the numbers, we've got 0.020 times 1/2 times 0.04077 pound mass per cubic foot. The density of air at 20,000 feet elevation times our 513.3 feet per second quantity squared times our frontal area of 225 feet squared. So this gives us a force of drag on the fuselage. Both of these forces, force of drag on the wing and force of drag on the fuselage, are horizontal forces, but our force of drag on the fuselage is then 24,169.4 pound mass feet per second squared. And again, we have to do our unity conversion ratio of 1 pound force for every 32.2 pound mass feet per second squared. Converting our mass acceleration into units of force in the U.S. customary system gives us 750.6 pound force is force of drag on the fuselage. Put a box around it, it's another answer that we were looking for. With these then, we can take our summation of forces in the x direction is equal to mass times acceleration, so that's Newton's second law there. We know if the aircraft is holding a steady velocity, then its acceleration is 0, and so we can say our force of thrust in the horizontal direction minus our force of drag on the wing minus our force of drag on the fuselage is equal to 0. Therefore, force of thrust is equal to force of drag on the wing plus force of drag on the fuselage. So our force of thrust then, force of thrust is equal to 3,493 pound force plus 751. We're just going to round up that 0.6 to 51 pound force. And we're going to conclude then that the force of thrust required by these engines is 4,244 pound force. Put a box around it and say, this is my answer. Now, kind of coincidentally, this is of similar magnitude of the power of the engines that we saw already, but that has units of horsepower. This is force, which has units, of course, of pound force. So we've filled in the next three calculations. We calculated the drag force acting on the wing, the drag force acting on the fuselage, and then the drag force acting or the thrust force required by all four engines to maintain a steady velocity. So each of these engines is providing just over 1,000 pound force of thrust, and all four acting together are providing that 4,244 pound force. Now we're moving on to the total mass flow rate through the propellers. And we've got two options here. We've got, on the one hand, if we focus on this cross-sectional area of the propellers, we've got our air velocity coming in like this, and then going out of the propellers, we've got our V2, our air velocity coming out. So we're going to look at if we were to use the quick way of just taking V1 and calculating mass flow rate, would that work for us? And then we need to look at the more rigorous way of using V2, which actually accounts for the power added to the propellers rather than just the power in the induced velocity of the air itself. So we'll kind of, again, take a look at the velocities and speeds that we need to work with. And now we're actually moving our control volume. Previously, our control volume was the entire aircraft, and now we're zooming our control volume into the engines themselves, taking them into account all at once, and using this force of thrust equation, as well as the mass flow rate is equal to density of the air, total area of the propellers, and then velocity of the airstream. Let me point out that this total area of the propellers for 4 propellers is 4 times the standard area of a circle in terms of diameter, pi-fourths, diameter squared. So first we need to calculate, well, on the one hand, we can calculate mass flow rate of the air using V1 with the information we already have, the density of air, the area of the propeller blades, and the velocity of the incoming air. But this method is incorrect. We're going to take the second, longer approach after we work through that and find out what V2 is, and then calculate mass flow rate using V2 in that case. But let's start with the easy approach. Mass flow rate, we'll just say m dot sub 1 is equal to density area V1. And so here we can use our density of air of 0.04077 feet, pound mass per feet cubed, times our area. So in this case, we've got 4 propellers, and then we do the area of each propeller, pi-fourths, times our diameter, so 13.5 feet, this quantity squared, times our velocity of 513.3 feet per second, and the product of these then gives us 11,982 pound mass per second is equal to m dot 1. Now, as I said, you may be tempted to use V1 to calculate your mass flow rate, but that'll give you erroneous results because the air hasn't been energized by the propeller blades until it passes through their swept area and goes downstream and becomes V2. Nonetheless, we'll retain this value just for reference for future, just to get a broader kind of exposure to the set of calculations. Now, in order to calculate mass flow rate using velocity 2, we're going to use the same equation, albeit with 2's for our subscripts, but we need to figure out how to calculate V2. It remains an unknown. But it turns out we can use that in the force of thrust equation to set up a quadratic equation which can then be used to solve for V2 given the force of thrust that we calculated in earlier steps. So here we can take our equation for thrust and then substitute in our equation for mass flow rate. In this case, we have density area velocity 2. By the way, this area is the swept area of the propeller blades, not the planform area or the frontal area that we use to calculate the drag forces. So knowing that our force of thrust is equal to mass flow rate, m dot 2, times this difference in velocity from downstream velocity V2 to upstream velocity V1, we can then equate that to the force of thrust, 4,244 pound force. But again, we need to convert our pound force to a mass times acceleration using the unity conversion ratio of 32.2 pound mass feet per second squared for every 1 pound force. And so this then returns us to the 136,657 pound mass feet per second squared that we saw earlier. Now we can take this equation and really rearrange it. So we're going to take these values here and rearrange them and say density times area times V2 squared minus V1 V2 is equal to force of thrust. And we can say, therefore, if we divide both sides by density area, we can say, therefore, V2 squared minus V1 V2 minus force of thrust divided by density times total area of all 4 propellers, swept area of the propellers, is equal to 0. Now, some of you may recognize that this is an equation in the form of ax squared plus bx plus c is equal to 0. And I know some of you have the quadratic equation memorized where we can solve for our unknown x, which corresponds to v. So I'm just going to say x corresponds to v2, I should say. And we can solve this using the quadratic equation, negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So this would allow us to solve for x using this equation, and we're going to apply that then to this equation where a is equal to 1, b is equal to negative v1, and then c is equal to that expression right there. So let's plug in some values. I'll rewrite the equation just to kind of keep it fresh on this page. V2 squared minus V1 V2 minus force of thrust divided by density area is equal to 0. And we can then say V2 squared minus, plugging in the actual value for V1, 513.3 times V2. Let me be rigorous in my use of notation. So feet per second times V2, that, minus 136,657 pound mass feet per second squared divided by 0.04077 pound mass per cubic foot times our 4 propellers with each having a swept area of pi fourths times 13.5 feet, in this case quantity squared. And so this then allows us to compact it down to V2 squared minus 513.3 feet per second times V2 minus 5,854.3 feet squared per second squared is equal to 0. And as we saw, that is of the form A V2 squared plus B V2 plus C is equal to 0, kind of a standard reference back to that square polynomial we saw earlier. Now, I do have to point out, we saw the conversion of pound force to pound mass right here. And if we work through these calculations, we'll see pound mass cancels pound mass. Feet cubed in the denominator jumps to the numerator. Denominator of the denominator jumps to the numerator, creates feet to the fourth, which is then canceled, 2 of which are canceled by these feet squared here. So this gives us units of feet squared per second squared. Now, if you didn't make the unity conversion ratio from pound force to pound mass feet per second squared, then this equation wouldn't be dimensionally homogeneous. We know that V2 squared has units of feet squared per second squared. Likewise, this second term has units of feet squared per second squared. If you didn't perform the unity conversion here, you would have erroneous results, and all your subsequent calculations would be faulty. So now let us proceed with our calculation and solve for V2. So here we've got V2 in the quadratic equation is equal to, let me remind you, negative b plus or minus the square root of b squared minus 4ac all over 2a. In the interest of time, I'm going to drop the actual units, but plug in the values. So 513.3 plus or minus the square root of 513.3 minus a negative, so plus 4 times 1, our value a, times c, our value of 5,854.3 feet squared per second squared, divided by 2 times 1. So this gives us a value then of 513.3 plus or minus 535.6 divided by 2. Now we know 513 minus 535 would give us a negative number, so we know that's unrealistic, and we'll just go with the positive number. In this case, of V2 is equal to 524.5 feet per second. This is kind of an intermediate calculation, but as I said, you need to use V2, the downstream velocity, to ensure you account for the energized flow. So continuing on then, we'll calculate our m dot 2. So m dot 2 is equal to density area velocity 2, which is equal to 0.04077, again, pound mass per cubic foot, times 4 propellers, each with a swept area of pi fourths times 13.5 feet diameter squared, and then times our velocity 2 that we just calculated of 524.5 feet per second. And so this gives us a mass flow rate using V2 of 12,244 pound mass per second is equal to m dot 2. So working through those calculations, we saw a mass flow rate using V1 gives us nearly 12,000 pound mass per second through all 4 propellers. And then using the V2 that we calculated from the quadratic equation, we get the slightly higher value of 12,244 pound mass per second. This is the value that we have to use, and V2 is the approach that we have to take for the final steps of our calculations. Now let's look closer at the engine again. So we're considering all 4 engines collectively as a control volume. We'll just say we're looking at a cross-section of 1. So we saw the aircraft traveling at 350 miles per hour induces this velocity of 350 miles per hour, or for our purposes, 513.3 feet per second, as our V1, the velocity of the aircraft, which we use to calculate lift and drag forces. And then using the conservation of linear momentum equation, we found that the downstream velocity based on the calculated thrust has to be something of the order of 524.5 feet per second. Now we have a known velocity 2, we already knew velocity 1, and we also calculated mass flow rate using velocity 2. So from this we could check and confirm that our thrust calculations are correct. So this then, at least would be used to calculate our thrust. We can use basically the thrust equation. Force of thrust is equal to m dot 2 times V2 minus V1, which is equal to our 12,244 pound mass per second, times 524.5 feet per second minus 513.3 feet per second, which is equal to 137,133 pound mass feet per second squared. And as we've seen multiple times already, we can't just use force with those units. We've got to take our force of thrust is equal to 137,133 pound mass feet per second squared times 1 pound force, which has 32.2 pound mass feet per second squared of mass times acceleration. And this gives us 4,259 pound force as our force of thrust using V2 for both velocity and mass flow rate. And that's approximately equal to the total force of drag, I'll say sub T, which we saw earlier was 4,244 pound force. So this is just kind of a check. Again, these agree within 15 pound force, which is well within the margin of error for these calculations. Now let's move on to sizing the engines, kind of the culmination of this set of calculations. In this case, we need to make use of the power form of the general energy equation for a fluid operating at steady state. And in this case, we can say we've got a horizontal flight direction, so our Z1 going into the engine is equal to Z2 coming out of the engine. Our pressure is atmospheric at that altitude, so P1 is equal to P2, given the size of our control volume. And then as we saw, V1 is a little bit less than V2 right here, but these are the assumptions that we're going to be using in this calculation. What I can say as well as is even though many jet engines are regarded as jet turbines, that's only accurate when we consider the control volume within the jet engine itself. For present purposes, the control volume we're looking at means it's effectively acting as a pump. It's taking in air from up front right here, it's energizing it, and it's increasing the energy, increasing the power of that air. So we're looking for pumping power of the 4 engines, which will then subdivide into individual engines, and it's not actually a turbine, so we're going to say no turbine is present, and then we're going to disregard mechanical losses as well. So, again, kind of what I had mentioned earlier, we've got our point 1, our upstream with its associated velocity V1, our point 2 downstream with its associated velocity V2. The point Z2 would be right around here, point Z1 would be up there, P2 right there, P1 right there, so on and so forth. And we're going to take this power form of the general energy equation and move it forward. By the way, our control volume is still being placed around the engine with sufficient boundary distance to avoid any of the complications associated with turbulence. Later in the semester, at least in thermal fluid systems design, we're going to draw our control volume around the jet engine itself, which is comprised of a compressor, a burner, and a turbine. In this case, it would be accurate to call it a turbine, but for present purposes, we're calling this a pump. So power of the pump. So going forward, we now need to make use of this general energy equation. We saw there is no turbine present, so we're going to say the power of the turbine is 0. We're going to disregard mechanical losses. We're going to say Z1 is equal to Z2, so these two terms just cancel out. I'm just going to zero those out there. P1 is atmospheric pressure at that high altitude, and P2 is atmospheric pressure. So these cancel out as well. And this then allows us to rearrange the equation to calculate power of the pump. In this case, all 4 jet engines or turboprop engines are equal to m dot 2 times V2 squared minus V1 squared over 2. And now if we plug in our values using our mass flow rate from V2, 12,244 pound mass per second, times 524.5 feet per second, quantity squared, minus 513.3 feet per second, quantity squared, divided by 2, we get our pumping power, that is to say the power of all 4 engines, is equal to 71,158,210 pound mass feet squared per second cubed. And we need to undo this with the unity conversion ratio again. So we'll do our 1 pound force divided by 32.2 pound mass feet per second squared. And so this gives us a magnitude of 2,209,882 pound force feet per second. Now that is a somewhat common unit of power, but it's not the unit that was requested in the actual problem statement. We want units of horsepower. So let's carry this through another conversion. Power of the pump is equal to 2,209,882 pound force feet per second times 1 horsepower, which has 550 pound force feet per second in it. And so this gives us a value of 4,018 horsepower. Now that's the fluid power that the engines have to provide to allow the aircraft to maintain that thrust and velocity that we saw earlier. So this is actually the power of all 4 engines, because we were basing our calculations on a control volume wrapped at first around the entire aircraft and then around all 4 engines at once. So we can then say the power, the fluid power of the engines acting as pumps on a per engine basis is equal to the power of the pump divided by the number of engines. So that's just 4,018 horsepower divided by 4 engines. And so this gives us 1,004.5 horsepower per engine. Now that's kind of an intermediate step. We're going to say W dot P comma E is 1,004.5, but now we need to take into consideration the efficiency of the propellers themselves. So just to kind of review a little bit, we've got our turbojet engine, we've got a shaft right here, and then we've got a propeller right here. We figured out that the power added to the air, W sub PE, for each engine is 1,004.5 horsepower. But if this propeller is 50% efficient, eta propeller is equal to 50% or 0.5, then we need to make that correction to figure out the shaft power of the propeller. So we'll take our shaft power, W sub P comma S on an individual basis, is our fluid power, WP comma E, divided by the efficiency of the propeller. Notice this is the English letter N, just for the number of engines. This is the Greek letter eta for the efficiency of the propeller. Be wary of conflating the two. So here then we've got 1,004.5 horsepower divided by 0.5, our 50% efficiency of the propeller blades. This gives us 2,009 horsepower, in this case shaft horsepower per engine. And this is typically how a lot of engines are rated in terms of shaft horsepower rather than fluid power of the engine. So this then is our 2009 horsepower per engine. Now we need to figure out the fuel power, a form of chemical power required for each engine to give it the range that it actually attains. So we saw fluid power, and the efficiency of the propeller was 50%. It takes shaft power from the engine and converts it to fluid power at 50% efficiency. We just calculated the shaft power per engine was 2,009 horsepower per engine. The fluid power was 1,004.5 horsepower per engine. Now we need to figure out how engine efficiency, in this case 30% efficiency, accounts for the fuel power. This is, of course, the JP4 fuel that we were interested in, and we need to figure out how that accounts for, or how much of that fuel power is coming in under those conditions. So fuel power, we're going to say fuel W dot, fuel per engine is equal to the shaft power of the engine divided by the efficiency of the engine. That is to say the Brayton efficiency of the engine, which is about 0.3. So this then gives us 2,009 horsepower per engine divided by 30% efficiency gives us 6,697 horsepower per engine in the way of fuel. We're on to the very last calculation, is how many gallons of fuel are needed to carry the aircraft 1,500 miles at 350 miles per hour. So now we can say total fuel power. So I'm just going to do W dot F comma T rather than on an engine basis, on a total power basis, is equal to 4 times our power of 6,697 horsepower per engine. And so this tells us the total chemical power, or the total fuel power of the aircraft, is 26,788 horsepower. And that's not the unit, horsepower isn't the unit of energy that the fuel is making use of, or also a unit of power that the fuel is making use of. So we're going to multiply by a standard conversion of 0.7068 BTU per second, so British thermal units per second, for every 1 horsepower. And this then gives us 18,934 BTUs per second of our fuel power. So power from fuel for all 4 engines, W dot fuel sub T, the total chemical power going into the engines to hold the velocity at 350 miles per hour and overcome the thrust force that we had seen earlier. Now, a chemical power equation, at least for volume flow rates, is W dot fuel total is equal to volume flow rate of the fuel times the specific energy of the fuel. And from this, we can then say the volume flow rate of fuel is equal to the power of fuel going into the aircraft times the specific energy on a volumetric basis of the fuel. So this then gives us 18,934 BTUs per second divided by 135,000 BTU per gallon. And so this then tells us we've got a volume flow rate of 0.1403 gallons per second. So another major kind of intermediate step. Now we just need to figure out how many seconds it takes for this aircraft to fly from, to fly this distance of 1,500 miles. So we can say, just kind of a very basic calculation, distance equals velocity times time. And we're interested, we could write that as, I don't want to use D for distance, I'll use DIST, because I don't want to conflate that with diameter of the propellers, is equal to V1 times time. And so from this we can say time is equal to distance divided by velocity, which is 1,500 miles in our very original problem statement, divided by 350 miles per hour. And so this then tells us it takes about 4.286 hours to go that distance. And then we can multiply that by 3,600 seconds for every hour and find that it takes 15,429 seconds of time to travel 1,500 miles at 350 miles an hour. Now, to calculate the volume of fuel required, we take the product of volume flow rate and time. And so this tells us we've got a volume flow rate of 0.1403 gallons per second times 15,429 seconds. And so this tells us it takes 2,163.9 gallons is equal to our total volume flow rate of fuel, the total fuel needed to go that distance, our final answer for these calculations. So we went through the calculations at the very start. We looked at a situation where we have an unloaded aircraft with its nominal lift coefficient at 0-degree angle of attack, provides a lift of around 75,700 pound force, which is pretty close to the nominal value of the empty aircraft. Then when we saw that it was weighed, loaded up to 150,000 pounds gross mass or total weight, it requires a lift coefficient of 0.1515 to stay in the air, and it has to fly at an angle of attack of 1.8 degrees. This gives rise to the drag coefficients and lift coefficients that we saw in the airfoil tables, and we found that the drag force is around 3,500 pound force. The drag force on the fuselage is around 750 pound force, and the thrust required to maintain velocity is just the sum of this plus this. That is to say 4,244 pound force. Then we saw that we cannot take the easy approach of using V1 to calculate mass flow rate. Rather, we have to use the thrust thrust equation and turn that into a quadratic equation to solve for V2 and thereby attain a mass flow rate of 12,244 pound mass per second. And then we were able to put that information in the general form of the energy, the power form of the general energy equation, and find, making use of the propeller efficiency, we were able to get the power of each engine is around 2009 horsepower, and then using that power consumption rate and the energy content of the fuel itself, we were able to get the volume flow rate of the fuel, and then using the volume flow rate of the fuel and the time to travel 1,500 miles at 350 miles per hour, we were able to get the total volume of fuel used. Now, earlier you saw that the engines were ranked around 4,500 horsepower, and you might ask, why did they oversize those by a factor of 2? Well, these type of aircraft also have to be able to take off with that fuel load and accelerate under relatively short runways, which is the topic of the subsequent portions of this case study.